Hope we're doing well. This is video 3 for the Algebra of Partial Fractions. Let's go ahead and do this example. We should notice that the denominator factors by grouping. The four-term nature of it should be an indication of that. Remembering, of course, when we put those parentheses there to change the sign of that last term, because putting the parentheses there is functionally factoring out that negative, okay? And so we have 5x plus 7. In that first, it winds up being x squared, x plus 2. In the second one, there's only a 1 that is common. And therefore, when I go to the full factorized form, we have, of course, x plus 2, and then x squared minus 1, which gives us x plus 1, x minus 1. Okay. Now, thankfully, this one is just another one of those easy with only linear denominators. The only challenging part about this is if you sort of fumble the factoring by grouping. So we have a over x plus 2 plus b over x plus 1 plus c over x minus 1. Let's go ahead and multiply through by the denominators. And we get a, x plus 1, x minus 1, plus b, x plus 2, x minus 1, plus c, x plus 2, x plus 1. Okay, well since we have all linears, we can use the Heavyset method with just the three convenient values, -2, -1, and 1. So let's go ahead and start with the convenient value of -2. So let's let x equal to -2. Now, of course, that's going to cancel out b and c. It's only going to give us an a term, and of course, this winds up being -10 plus 3, so -3. And then, of course, -2 into here is -1, but -2 into here is -3, and so that winds up being -2 into here, -1, -2 into here is -3, so that winds up being a is equal to 6. Right? Yeah. Okay. Yeah. Just no, not 2. -1 and -3. So that winds up. Those go bye-bye. These negatives, and so a is equal to -1. Okay. We need to let x equal -1 in order to find b. So that's going to basically cancel out those two terms. Plug in -1 into here to get -5 plus 7, which is +2. -1 into here is going to be +1 and -2 times b. So b is equal to -1 as well. Okay. Let's go ahead and let x equal +1. And that winds up being 12. And that's going to cancel out both of these. And all we're going to get is here. So it's going to be c times 3 times 2, so that's going to be 6c is equal to 12, or c is equal to 2. And therefore, what we have here is we have -1 over x plus 2 plus -1 over x plus 1 plus 2 over x minus 1, and that is our decomposition. Okay. Now, let's sort of summarize what we've learned thus far. Okay. Insofar as types of factors in the denominator, and I'm not going to draw a specific numerator, let's just put p of x for some polynomial. If we have, x minus 1, and then x plus 2 squared, and then x squared plus 3, we have a linear, we have a repeated linear, we have an irreducible quadratic. Okay, well, let's go ahead and do, that winds up being a over x minus 1. The linear is pretty straightforward. The repeated linear winds up being b over it squared, and then another over it to the first power. So this is, of course, how we handle repeated linears. And then over the irreducible quadratic, I need to represent it as a linear, even if it may not wind up being a linear, because of that, because there's the possibility of it, right? I mean, d could be equal to 0, e could be equal to 0, they could both have a value, who knows, right? But of course, I mean, there are further iterations. You could have something that had, you know, x plus 2 cubed, okay, and then x squared plus 3 squared. Okay, well, let's deal with the repeated linear right here. That's not raised to the second power, that's actually raised to the third power. So we would need a over x plus 2 cubed, and b, you just step down twice instead of stepping down once. And that winds up being how you handle a repeated quadratic, a repeated linear. Now here we have a repeated quadratic. Well, if you sort of blend both of these strategies together, you should, you know, it's probably a little bit predictable. You get dx plus e over x squared plus 3 squared, and then fx plus g over x squared plus 3. And that is how you deal with a repeated irreducible quadratic. And so, you know, there's a little bit of wiggle room. Not wiggle room, but basically there's a little bit of overlap between some of the strategies when you have something like that. Okay. Now, in terms of strategies, there are really 3 that we've seen, and 2 of them kind of overlap because both of them deal with systems. Okay, potentially at least. One is what we call the Heavyset method, or what I continually refer to as convenient values, right? Convenient values. They're the ones that make, once I've multiplied everything through by that common denominator, they're the values that turn some of those factors into zeros that make it easier for me to find some of those A, B's, and C's that we're looking for to populate those numerators. So we have the Heavyset method. We have the, what I've referred to, since I don't know any other name for it, the coefficient comparison method, okay, which sometimes it can lead to a system of equations, okay. Sometimes it doesn't. And then, of course, there is the, you know, and I don't know the official name for this one either, basically plugging in random x values, okay? And that is specifically for the sake of leading us to a system of equations, okay? And of course, some of the problems that we deal with wind up being a combination of these, right? We can use convenient values for 2 of them, but then we need to resort to coefficient comparison or plugging in random values in order to find the balance of them, the rest, okay? And that's, you know, so basically you need to know how to deal with the particular factors from the denominator, especially as if they're repeated. And then you need basically to be able to employ all 3 of these strategies, oftentimes in concert with each other, to actually find the decomposition that you're looking for. Now, this one, I'm not asking you to solve this one. This one, we just need to go ahead and try and figure out how to pull it apart, okay? This is a repeated linear. This is an irreducible quadratic. This is a repeated irreducible quadratic. So what happens here is for the repeated linear, we get that. So that comes from the x. Now, this is an irreducible quadratic, so we simply need a linear, sorry, that needs to look like an e, over it. This is a repeated irreducible quadratic, so we need a linear over it squared, and hx plus, we'll call it j, over x squared plus 2, and that, of course, comes, oh, that's cubed, wow, not squared, so I didn't see the cube, I thought it was a square, I wasn't looking that carefully, kx plus l over x squared plus 2, and there you go, okay? That is how you would basically expand this one out if that's what you were given. Let's go ahead, there's one more, this one doesn't show it, but after this there's going to be one more little wrinkle that we need to talk about. But let's talk about this one. This basically is a problem with 2 irreducible quadratics. And so we have 2x cubed plus 7x plus 5 over x squared plus x plus 2, and then x squared plus 1. I'm going to get ax plus b over x squared plus x plus 2. Now, what's new about this is we actually haven't done one where we couldn't use the Heavyset method at all, right? Nothing is going to happen here with the Heavyset method. What we need to do instead is we need to figure out another strategy, okay? So we're going to go ahead and multiply through, and we get 2x cubed plus 7x plus 5 is equal to ax plus b times x squared plus 1 and cx plus d x squared plus x plus 2. Now, you can start plugging in values if you would like, or you can multiply it out and basically reorganize to do coefficient comparison. I tend to like coefficient comparison simply because when it comes to systems beyond 3 equations of 3 variables, there's just so much going on there. There's so many places to lose numbers and negative signs and stuff like that. So this one, let's go ahead and multiply it out. Ax cubed plus bx squared plus ax plus b plus, and let's do cx times that trinomial. Cx cubed plus cx squared plus 2cx, and then d times that trinomial, dx squared plus dx plus 2d. Third degree, second degree, first degree, third degree, second degree, first degree, second degree, first degree. And by the way, if you don't do that, if you don't have some sort of indication in terms of getting together like terms on something that large, I recommend that. It's, you know, I don't know where I picked it up, but it helps me to sort of organize my thoughts, so I can kind of go through. And I'm looking for second degree now, and I see the fact that there's 1, 2, 3 of them because I've already underlined all 3 of them twice, and I get b plus c plus d x squared. And now let's go back to the linears, a and d and 2c, a plus d plus 2c x. And then, of course, the constant is b and 2d. b plus 2d. And, of course, that is equal to 2x cubed, 0x squared, plus 7x plus 5. That means that a plus c is equal to 2, b plus c plus d is equal to 0, a plus d plus 2c is equal to 7, and b plus 2d is equal to 5. Now, that is a system, okay? And you can stack it up if you really want to and treat it like that. But, I don't know, you may not want to. Let's go ahead and let's basically group these two and group these two. So I have a plus c is equal to 2, and I have a plus 2c plus d equal to 7. Now, of course, I can use this, if I multiply this one through by a negative, to actually get rid of the a and give me c plus d is equal to 5. This one right here, I have b plus c plus d is equal to 0, and b plus 2d is equal to 5. Now, if I multiply this one through by a negative, and of course, you know, negative 0 doesn't make any sense, but you get where I'm going with this, I get negative c plus d is equal to 5. Well, that has allowed me to basically get c plus d is equal to 5, and negative c plus d is equal to 5. That gives me 2d is equal to 10, or d is equal to 5. Fantastic. Well, if d is equal to 5, then from both of these, we obviously can surmise that c is equal to 0. Okay. Now that I've got c and d, it ought to be pretty easy to find a and b. C can go back into this a plus c. So if a plus c is equal to 2, a plus 0 is equal to 2, a is equal to 2. Okay, well, then that means that b plus c plus d is equal to 0, and therefore b is equal to -5. Okay, so I have a 5, a -5, a 0, and a 2. Let's go ahead and plug it back in up here since we've sort of run out of room down here. We have 2x minus 5. And then c is 0, so all it is 5 over x squared plus 1. And will you look at that? Yay! Okay. Now, that is my decomposition. The next wrinkle that goes into this, and you're saying, oh boy, is this. Now, I need you to stop and at least think for a second about what might be different about this particular one. And it's the fact that it's top-heavy. Okay? It is an improper fraction. And as an improper fraction, we cannot do the decomposition until such time as we actually do the division and reduce it. Now, if you do the division, and I'm going to spare you that, and if you need a little bit of review on polynomial division, then we can chat about that later. But you get 2x minus 7, and you get 18x plus 19 as the remainder. And of course, as the remainder, it remains over the original denominator. And so what we want to do is we want to do the decomposition with the remainder expression. And we get a over x plus 1 and b over x plus 2. We get 18x plus 19 is equal to a times x plus 2. And basically you just go on and do it the way that you normally would, but you just have to remember to do the division first, because otherwise it just doesn't work. You get -17 and b times -1, so b is equal to 17. And when you let x is equal to -1, you wind up getting 1, because it's -18 plus 19, right? And you get a times a times 1, and therefore a is equal to 1. So the actual true decomposition includes the quotient, that linear quotient, plus a over x plus 1, and then of course b over x plus 2, and there is your answer. But you have to do the division, okay? You have to do the division. Now, we're just going to do it one more time, and on this one, I may actually do the division for you since, you know, it's probably been a heck of a long time. Now, when you're only dividing linears in, obviously you can use synthetic. When you're not doing that, you have to go ahead and make recourse to the old school. And we have x cubed plus 2x squared minus x plus 1. And how many times does x squared go into x cubed? Well, it goes in x times, and then you multiply it minus 4x, and then of course you subtract all of those, and it's x cubed minus x cubed, which is 0. That was kind of the point. 2x squared minus 3x squared, so -x squared, and -x plus 4x, so plus 3x plus 1. How many times does a x squared go into -x squared? -1 times. -x squared minus 3x plus 4, but then of course you're subtracting, and so 6x minus 3. And so what we have here is we have x minus 1 plus 6x minus 3, and we'll go ahead and do the factorization. That's x plus 4 and x minus 1. So basically from here we need to just concentrate on the remainder expression. We have a over x plus 4 plus b over x minus 1. Let's go ahead and multiply through and by the common denominator so that we're getting rid of the rational expressions. Let's go ahead and let's let x is equal to 1. If we let x is equal to 1, we're going to get 3 is equal to b times 5. So b is equal to 3/5. Now, we've done fractions before. It's not that big of a deal. So let's go ahead and let's let x is equal to -4 this time, right? And therefore, we put in -4 into here, we're going to get -27. Of course, this b term is going to go bye-bye, and we're going to get a times -5, and therefore a is equal to 27/5. Okay, well, you know, have the same denominator. So what we have here is we have x minus 1 plus 27/5 over x plus 4, and then plus 3/5 over x minus 1. But we usually want to get rid of those fractions, so we'll pull the 3/5 out and just leave it as 9 over x plus 4 plus 1 over x minus 1, and this is our decomposition. Okay. Now that is 3 videos, and of course the older one that I'll leave in the playlist. It's 3 videos plus tons of examples. I'm going to not only post these video pages, but your homework will have an answer key to it, and I'll see if I can post any other additional things for you to sort of look through at your leisure and if you need it. As always, if you have any questions, please do shoot me an email. Bye.